Okay, good afternoon, guys. Give your attendance in the chat box. There was some issue from my side, so that's why the class was delayed for 15 minutes. I'm waiting for others to join. I'll start in next 2 3 minutes because I know a lot of people will join this. So I'm waiting for next 2 3 minutes. Then we'll start. Okay. Anyway, okay. Let's wait for two more minutes. 2 more minutes. Let's wait. I don't want people to come at 1:40 and then ask me what I'm doing because this is a revision class. So I don't know why people are not joining. Okay, let me start. Let me start with definition of charge. And So I have told you charge is presence of, or let me start with atomic level. So suppose I have small atom, and in or let me make a bigger one for you so that you can understand. And atom will have positive protons and same number, and then few neutrons would be there, and same number of electrons would be moving around it. So what happens is that if these electrons get some energy which is capable enough of getting them out of their orbit in which they are revolving around the proton, the electrons will come out. Conventionally, electrons are denoted as negative charge. So I will tell you from here that conventionally we have two types of charge. One is positive. So generally, nucleus which contains protons is denoted as positive charge. So when I'm and negative charge is electrons. So this is just convention that this is positive and this is negative. And I have to also told you in the class that positive charge, it denotes that not deficiency of protons. Protons in the nucleus remain same. So what do I mean by positive charge then? So positive charge is just deficiency of electrons. It means that out of the neutral atoms, few electrons have jumped out of their orbits and they are no more revolving around the protons or the nucleus, which makes the atom neutral, and they are not in their orbit. They have got some energy from some other source and they are wandering somewhere else. So, free wandering of the electron is known as presence of charge at at any particular place. Now from charge I started teaching you. After charge I started teaching you that this was the charge. Now there are few characteristics of charge, like we have few characteristics of uh, any particular element like mass, charge. These are intrinsic characteristics. One is mass, second one is charge. So when I have electron and if it is free electron, so I have charge on it, and the charge is supposed to be 1.6 into 10 to the power minus 19 coulomb. Now there are few more things, which is like first one is charge is conserved. So what do I mean by charge is conserved? So try to understand, if I have atoms, so suppose I take any particular object, it will be made of billions of atoms. And when I say atoms, atom is combination of proton and neutrons in its nucleus, and number of protons would be equal to number of electrons in a neutral atom, and there would be billions of such atoms. Now what happens if I give some energy to these electrons, and even if they come out, we are not creating any new electron or proton. The electrons from its orbits are jumping out of it, and they start moving freely around that particular object, whatever space that is present over there. You can understand the size of electron is very very small, so they don't I mean they can sneak through the object because of their very very small size. And due to this, there is a property which is like charge is conserved, by which I mean to say that in an atom, number of protons are equal to number of electrons. Even if electrons are jumping out of their orbit, we are not creating any new electron. So suppose I have any particular atom Z, and if Z has n number of protons, so neutral Z will have n number of electrons also. And now what happens if two electrons comes out of here? So Z becomes 2 positive. Z becomes 2 positive means two electrons have left the orbits of Z. Now these two electrons are moving freely somewhere else. But if we add the number of protons, total number of protons and total number of electrons, they remain same inside that object. Inside the sorry. So it means that the charge is conserved in that manner. The second thing is charge is quantized. And what do I mean by charge is quantized? So what are the charged particles? Charged particles are electrons and protons. And try to understand, uh, any time charge would be an integral multiple of charge of one electron. Now this particular sentence may look like a very heavy sentence or very difficult to understand, but I would like to explain it in this manner. So try to understand, when one electron comes out of the the atom becomes one positive, and the charge is charge equivalent to charge available on one electron. Now the number of electrons coming off the out of the orbit would always be integers. I am saying the number of electrons. It will never be the case that two and a half electrons come out of the orbit. It will always be either one electron or two electron or three electron or four electron or five electron likewise. So the number of electrons which are coming out of their orbits and moving freely are in integers. And that is why the charge is written like n into E. Now, what do I mean by n into E? So, E is generally denoted as charge on one electron. So, this E is 1.6 into 10 to the power minus 19 coulomb. Now, if 150 electrons are moving freely inside a particular piece of object, so then the total charge would be 150 E. That is why I am saying that the charge is quantized. So charge quantized means the charge of any object would always be an integral multiple of E. That's what I mean. Why it will be an integral multiple of E? Because the number of electrons which will be moving freely inside a particular object will always be in integers, and that is why charge quantized means Ne. So I hope you understood this. Now I'm moving to another concept, which is Coulomb's law. So by Coulomb's law, I have taught you this. So this is written as Coulomb's, but it is called as Coulomb's law. Now you all might have because this is a revision class, so I can discuss a few things which I have discussed in the class time and again. I tell you that suppose I have to shift my almirah from one place to another place. I have to apply some physical force on the almirah so that that almirah can be shifted from one place to another. But what happens is when two charges are kept in near vicinity, or if two charges are separated by a distance r, then we see some kind of force being applied on those two charges. My question is, those two charges are not touching each other. So from here, two questions arise. What are those two questions? First, from where does that force eliminate? From where does that force comes into picture? So, like if I have two charges, if I denote it here, and this is my charge, positive charge Q1, and this is my positive charge Q2, and there is another case where I have a positive charge Q3 and a negative charge Q4, and I have another force where I have a negative charge Q5 and another negative charge Q6. Now my question is, there are two things. Once when the charges are not touching each other, when they are separated by certain distance, how force is originating, and if force is there, and if the charges experience certain force, what is the magnitude of it? So first one is, I'm answering the second question and then I'll go to the first question. So the magnitude of force is given by F is equal to K Q1 Q2 divided by R square. So it means that force is proportional to the charges on them, and force is anti-proportional to the square of the distance between them. And what is this k? K is called constant. The value, the k is written by 1 by 4, 1 by 4 pi epsilon naught, where epsilon naught is permittivity of free space, or permittivity of I'll explain this permittivity constant. K is the value of k. When you put the value out here, I'm writing the value of epsilon naught here. It is 8.85 into 10 to the power minus 12. And when you put these values here, you get k is equal to 8.99 into 10 to the power 9, which I also call 9 into 10 to the power 9. So you can use any of these values, doesn't matter. Now try to understand why I have made these three cases. So if you put these values here, of q1 and q2, if both of them are positive, anyway distance is positive and k is a positive constant, so force would come out to be a positive. If one of them is positive and one of them is negative, so force will come out to be negative. If both of them are negative, then again negative negative will get multiplied here and it will be positive. It means that, try to understand it, it shows me that if force is positive, and what do I mean by force is positive and force is negative? So force, as we all know, is a vector quantity, and if force is a vector quantity, it in for any vector there are two properties. One is its magnitude and second one is its direction. Now I'm not bothered about direct magnitude here. Magnitude anyway is given by k q1 q2 divided by r square. But what do I mean by this positive and negative force? It means that direction of two, there are two kinds of I mean two directions for these forces. One is positive direction and one is negative direction. It means, and we can also see that when the charges are of same type means magnitude of the charge may be different, but when I say that the charges are of same type, I mean to say that the charges have same sign. And if charges have same sign, then the force is coming out to be positive. When both of them are positive, the force is positive. When both of them are negative, then also the force is positive. But when the charges are of different sign, when the one charge has positive sign and the another charge has negative sign, so then in that particular case the force becomes negative. It means that the direction of the force changes. So this tells me that the force applied between the different kind of charges are of different nature. And from here we come to a conclusion by experimenting this, that two like charges repel each other and two unlike charges attract each other. So this concept of force being positive and negative tells me that the direction of the force between two charges when they are same is away from each other. So this particular charge q1, when it will apply force on q2, so suppose it applies force f1, f1 would be away from this. If I draw a line from here, f1 would be away from charge q1, and if this applies force f2, f2 would be away from charge q2. So this is a force of repulsion. Similarly here, but in case of q3 and q4, which are of different signs, or one positive and one negative, if I draw a line joining them, q3 would be a force of, f3 would be a force of attraction, and similarly f4 would be a force of attraction. So two like charges repel each other and two unlike charges attract each other. This is what Coulomb's law is all about. I hope you understood it. Okay, so somebody asked me why charge is quantized. I'm saying that, let me go to the first thing. Charge is quantized because what I'm trying to say is a charge is when the atom does not remain neutral. It means that few of the electrons jump out of their orbit and start wandering freely around the space available. Now number of electrons jumping out of the orbit will always be in integers. So it will never be the case that 3.5 electrons jump out of the orbit. It will always be 2 electrons coming out of the orbit, 3 electrons, 150 electrons are in roaming inside some space. So that is why the charge would inside an object will always be written as n into e. It means that charge on one electron multiplied by number of electrons roaming around freely inside a space. And that is why I'm saying that charge is always quantized. It can be quantified in terms of, or the total charge can be quantified in terms of number of electrons roaming around uh, in an object. I hope you understood it. Did you understand, Sutti? Tell me, I'll move ahead. Okay, I hope she understood it. Now let me move to electric field. So the first question was, when two charges are separated by certain distance, how they are able to exert force on each other. So my question was that if I have an almirah at my house and I want to put it from a place A to B, what I'll do is I'll have to exert a force, physical force on it. and then if the force is able to overcome the friction that it is already having, and the inertia, so in that particular case, then I'll be able to move this almirah from place A to B. But what happens is, if two charges Q1 and Q2 are separated by a distance r, and there is no physical contact in between them, still they are exerting force on each other. How this is possible? To explain this particular phenomenon, there is a concept of electric field, and I have discussed this in the class also, that whenever we have to explain a force where physical contact is not happening, we try to explain it with presence of field. So what we say that is, this particular or any charge, what is electric field? Electric field is a mathematical definition. I'll give you, I'm giving you now. Electric field is defined as force applied per unit charge, but this does not explain the concept very well. So let me explain the concept. What happens is any particular charge, if I have, we assume that the charge creates electric field around it. Now what kind of electric field it creates? So electric field is generally denoted by electric field lines. So try to understand, if I have a positive charge q1, it is assumed that electric field is created with the help of electric field lines, and if charge is positive, electric field lines are conceived to be coming out of the electron, something like this. Then if a charge is negative charge, electric field lines are conceived to be going towards that particular charge. So then, if electric field lines are defining me the creation of electric field, and hence the application of force, how does that phenomenon happens? So try to understand, all of you, that due to this charge, wherever there would be a presence of these electric field lines, the charge will be able to create its own electric field, and due to its own electric field, if any other charge comes into the if any other charge comes in contact with the electric field lines of charge q1, then that other charge will feel certain force in the electric field of charge q1. What I say, that if charge q1 is here and it is sending outward electric field lines, something like this. Now what happens, there comes a positive charge q2. Now what happens, this charge will also be sending electric field lines outside. Now what happens, how the interaction of field lines will happen here? So let me explain you interaction of field lines. There is one possibility that this field line goes and touches this charge q2, but what happens if there is another, if there is a field line from charge q1 which is going and merging with q2, then you see here, if charge q2 is positive, all lines are going out, but this line is going and merging with q2, which is against our convention. So in that particular scenario, what it is assumed, that when two positive charges are interacting with each other, then there would be a place where these field lines will never interact, and these field lines will move away from each other, because moving towards each other would mean that this field line and is going and merging with charge q2, and field line emerging from q2 and is going and merging with charge q1. It means that there would be one common line which is going towards positive charge. As by convention we know that there is no line which goes towards positive charge. All the field lines comes out of the positive charge. Hence the field lines are represented like this, and that is why there is a force of repulsion between two positive charges. So the field lines interact in such a way that the field lines from two positive charges will never cross each other and will always move away from each other. That's why between two like charges we have force of repulsion. If I have a positive charge and I have a negative charge, then the case is simple, because a charge will a field line will come from here and can go and merge over here, because all the field lines come and converge on the negative charge. The field lines diverge from the positive charge. So a charge which is coming out like this will go and converge on negative charge. Similarly, a field line coming out like this will go and merge here. So there is a force. All the field lines from positive and negative charge do cross each other, and they diverge from positive charge, converge on negative charge. That is why there is a force of interaction over there. Now, what is the magnitude of electric field? Let me come to that part. So magnitude of electric field is given like this. So if this is the charge q, and at this distance r, suppose this is point p at distance r, how much electric field it will produce? So we keep a 1 coulomb charge over there. So I told you that electric field is force applied per unit charge. Per unit charge means if I keep a 1 coulomb charge, or a unit charge, a 1 coulomb charge is also known as a unit charge. So if I keep a unit charge here, so force applied would be equal to k q into 1 coulomb divided by r square. So if I divide this charge by 1 coulomb, divide this force by 1 coulomb, so force divided, this 1 coulomb goes here, is equal to kq divided by r square. So force per unit charge is known as electric field. So electric field is kq by r square. Now, before I explain it with non-unit charge, let me tell you that what is this q. This q is charge because of which I want to know the magnitude of electric field. So electric field is property of the charge which is creating it, not the property of the charge on which it is exerting the force. Try to understand. I'm trying to tell you electric field is property of charge which is creating it, and not the charge on which the force is getting applied. So suppose what I have is, instead of this 1 coulomb, I have a charge q1 here, or a charge q here, and suppose I take this as q1. So force applied on q would be f k q q1 divided by r square. Now force applied per unit charge, I mean, what is the force applied if q1 becomes 1 unit? So that would become f by q1 is equal to kq by r square. So try to understand, look at here. If I keep 1 coulomb charge here, or if I keep q1 coulomb charge here, the electric field remains kq by r square at distance r. So that is why I have been telling you this, that electric field is property of charge which is creating it, not the charge on which it is applying the force. So try to understand now, electric field is proportional to amount of charge. An electric field is anti-proportional to square of the distance from which I am trying to calculate it. So try to understand that if the distance from the charge is increasing, then the amount of electric field will go down, or the magnitude of the electric field will go down. So if uh, understand here, if this is charge q, so the amount of the magnitude of electric field here at point P, and there is one point here, I can say that EP is greater than EQ just by looking at it. Why? Because distance from the charge, suppose this is R1 and this is R2, so R1 is lesser than R2. So magnitude of the electric field from any particular charge will keep on reducing depending on the distance, I mean depending on as the distance is reducing, going away from the charge. So this is the concept of electric field lines. Now let me move to electric potential. Do you understand electric field? Yes, no? Now give me a moment, guys. I'll be just back in one moment. Okay, so before I teach you electric field, sorry, electric potential, let me discuss potential energy with you. So in grade 9, you all might have studied gravitational potential energy. So in that particular concept, you might have studied that if this is the ground level, and here if I assume this is ground level, so here, if I assume ground level means I'm assuming H to be zero. So if here I assume potential energy to be zero, if here I assume potential energy to be zero, so at any particular height H, my potential energy or the no, not my potential energy, the object's potential energy was mgh, where m was mass of the object, z is gravitational acceleration, and h is height. Now why this potential energy? So look at here, there is I'm not getting into much details. uh, Work done is always defined as change in energy, as kinetic energy. Once again, change in energy, As kinetic energy remains same, what is kinetic energy? Kinetic energy is half mv square. So mass is there but velocity is not there, or speed is not there, so I am assuming that my object is at rest at both the points, so there is no change in kinetic energy, hence work done would be equal to change in potential energy. So which is nothing but work done is equal to mgh minus 0, because I'm assuming potential energy to be equal to 0 and work done is coming out to be mgh. Now why am I doing all these things? Try to understand a lot of when you were learning potential energy, concept of potential energy, there might be a line which was written in the book, or which you might have studied while doing this concept, that potential energy is dependent on position of the object. Now generally if you see, potential energy is a notional concept. So what do I mean by notional concept? So try to understand here. uh, Kinetic energy is actual energy, like which comes due to its speed, but potential energy is considered to be energy which is stored inside a body because of its position in the space or in the universe, or in a plane or in a three-dimensional plane. Likewise, whichever term you want to use, you can use it here. So why potential energy is stored in a body? Because of its position, because it is assumed that at infinite the potential energy is considered to be zero. And if at infinite the potential energy is considered to be zero, what happens over here is that if an object is kept at its place p, and forget about this ground level thing now. If at infinite the potential energy is zero, and from infinite I am bringing that object to any particular point p, I'll have to do some work to bring this particular object from infinite to this particular point p, and due to which, as the work is done on this object, some amount of energy would be stored in that particular object. Now I know that work done is equal to force into displacement. So if work is getting done, certain amount of force is applied on that body, and if force is applied on that body, some amount of stress would be there in that body, and due to that some amount of potential energy would be stored out there. This is why this concept I apply in electric field also. So what it is done is, so try to understand, look at here, if I have a positive charge over here, now what does this positive charge do? The positive charge, because of its intrinsic characteristics of having a charge, will have its own electric field, and I call this electric field lines, presence of electric field lines around a positive charge, as stress zone. Why it is stress zone? Try to understand, because if you keep any kind of charge over here, the charge will undergo an stress, or a charge will experience certain amount of force. Why charge will experience certain amount of force? Because of presence of this electric field line created by this positive charge q, and due to that force some kind of displacement will happen, and hence position of the object will change. Now try to understand, look at this point p, here the electric field is E1, and look at this point q, here the electric field is E2. Now try to understand, as E1 is greater than E2, the stress zone at point P, or amount of stress or amount of potential at point P, would be more than amount of potential at point Q. Why? Because here the magnitude of electric field is more and here the magnitude of electric field is less. Hence the ability of this point P to apply force on certain other charge is more than ability of this point Q to apply force on any other charge. Are you understanding? I'm again repeating what I'm saying. At this point P, this point has more ability to apply force on certain charge than this point Q, because the magnitude of electric field, that this stress zone, if I draw this circle here which is equidistant from this charge Q, and if I draw this circle here which is also equidistant from, so suppose this is R1 and this is R2. So from, as distance R1 is lesser than R2, at distance R1 more force would be applied because the amount of electric field is more. Hence at this point the all the points will have more potential to apply force than any point at this particular circle. So potential is generally written as 1 by 4 pi epsilon naught. I'm not getting into derivation, multiplied by Q by R. What is Q? Q is the charge which is creating the electric potential or electric field, and R is the distance of point at which I am calculating the potential. So V is proportional to Q and V is anti-proportional to R. Did you understand the concept of potential? Yes or no? Tell me. I want answer from all of you. Whosoever is there, answer. Okay, great. So now try to understand. Um, all of you are sitting with the. So let me explain one formula to you. I already told you. So work done is equal to change in potential energy when kinetic energy remains same. I mean, so try to understand work done over here is potential energy is given by at any particular point. So if I take this point and I ask you what is the potential energy here, potential energy or electric potential energy is given by Q into V of certain point. V means potential of electric potential of certain point. So this is the potential energy. So work done is equal to change in potential energy. So suppose the potential over here is VA and potential over here is VB, and I am transferring a charge Q from VA to VB. So work done will be equal to uh, potential energy here. So potential energy UB minus UA. UB would be equal to Q into VB minus Q into VA. What is Q? Q is the charge which is getting transferred from one to another place. Q is not the charge which is creating potential energy. Try to understand once again. Q over here in this formula is not the charge which is creating potential at A and V. Q is the charge which is getting transferred from A and V. Some other charges are creating potential at point A and V. That is why I am calculating VA and VB. So Q W would be equal to Q multiplied by VB minus VA. Now let me go to, so this was electric potential for you. After electric potential, I taught you what? I taught you, I went directly to, after static, I went directly to current. So let me explain you now current, electric current. So electric current is given as, the definition is charge per unit time is known as electric current. So I is given by, I is equal to Q by T. And what is Q? Q is equal to NE. So I can also be written as I is equal to NE by T. Generally Q would be given to you. So I is equal to Q by T. Now try to understand. So now let me go and calculate the another concept of. So suppose I have a wire like this. Generally the wire is considered to be cylindrical. So how do I come to know that? So try to understand here. Now how will you count that? How much charge is there in this wire? So why I want to calculate this? Because I want to calculate, objective is to calculate the current density. Sorry, yes. So to calculate the current density of a wire. So what I do is try to understand. Suppose, look at here how I am doing it. So suppose this is this cross sectional area is A. So suppose cross sectional area of the wire is A. Why I'm taking cross sectional area? Because I want to give you electron density. And what is electron density? Electron density is number of electrons per unit volume. So suppose electron density is equal to n. So try to understand what is current density. Current density is denoted by capital J, and it is defined as current per unit area. So J is defined as I divided by A. So what I need to do, I need to find out I. I know that I is equal to, try to understand, I know that I is equal to Q by T. And what is Q? Q is equal to Ne divided by T. What is N? N here is number of electron. But I am not giving you number of electron directly. I am giving you electron directly. Sorry, electron density. I am not giving you number of electron. Try to understand. I am doing it on the other side. If if number of electrons are given directly in place of, I have explained this concept in the class, I think, in place of, if number of electrons are given directly in place of electron density, then J can be written as J would be equal to Ne divided by A. That's the formula, nothing else. This is the formula where N is number of electrons. But why I am giving you, try to understand why I am giving you number of electron, I mean no, why I'm not giving you number of electrons directly and I'm giving you electron density, because I want to explain you a concept of drift velocity. And what is drift velocity? Try to understand. Drift velocity means, so it's something like this. Try to understand. So suppose this is certain space in which electrons are moving from one place to another place. Now electrons don't move in one particular direction. So their direction of speed would be something like this. So it will be moving in jigsaw, I mean in some random motion of electrons. They'll not move in one particular direction. So if they don't move in one particular direction, so then what happens? Try to understand what the concept of current that is I started teaching you. I started teaching you from the mathematical perspective of it. So to calculate what is the electron, how to calculate the electron, the conceptual basis on which the electron should be studied is something like this. Try to understand, if this is my wire, and if there is no external energy provided to this particular wire, by external energy I means if there is no electric uh, potential across, or if there is no battery connected across this wire, there would be no current in it, even if number of free electrons are present in this conductor. Why? Because the electrons present in this, suppose these are electrons, few electrons, the electrons present in this particular conductor would not be moving in one certain direction. They would be moving in this random fashion, and that overall movement will cancel itself, and the electron would be sorry, and the current would be zero. Also they'll collide with each other, they'll be losing their energy, and all sort of impact will happen, and due to that their effect as effect would be, I mean, effect of the motion of the electron would be zero. Now when you apply certain potential across this particular conductor, what happens? All the electrons start moving in one particular direction, and the speed at which they move is known as drift speed. So what is drift speed? Drift speed is the speed of the electron in which it is moving in one particular direction under the effect of certain potential energy applied across the conductor. So this is what the drift speed is. And drift speed is proportional to, so you may ask that if I change the electric potential, will it change? Yes, it will change. Drift speed is proportional to the electric field applied. And I know, we know that how electric field is related to the potential. So if I'm saying that if the potential is increasing, it means that in between these 2 points there is a higher potential difference. This drift speed would be something else. If we decrease it, the drift speed will also decrease. So try to understand, I gave you current density here to explain you this drift speed. Now how it is utilized to find out current density is that if the cross sectional area is A, so, and if drift speed is Vd, if I assume it to be Vd, so in t time how much it will go? It will travel a distance of Vd into t. So what would be the volume? Volume is area multiplied by length. So area I have already given you A, and in t time the length covered by the electron would be Vd into t. So this is the volume. Now number of electrons in this, try to understand, number of electrons would be equal to current density, sorry, electron density multiplied by volume. What is electron density? It has been given to me as N, and volume I have calculated as A into Vd into T. So this is number of electrons. So I'm negating this. I'm writing it, negating this multiplication sign. I'm writing it Na Vd T. Now these are the number of electrons. Now I told that the charge is quantized. So charge Q would be equal to number of electrons multiplied by E. What is E? E is my charge on one electron multiplied by total number of electrons. So I can write it as Na Vd T into E. So remember this, if I am asking you charge and I am giving you current density, area, drift velocity, time, you should understand that this NaVdT is nothing but number of electrons when charge density is given. Here N is not number of electrons. Here N is number of electrons per unit volume. That is why I'm repeating it time and again. I have told you charge is quantized, and I have told you that Q is equal to Ne, where N is number of electrons multiplied by charge on one electron. Here I am saying you that charge is Na Vdt into E. Don't get confused with this N. Here N is not number of electrons. Here N is electrons per unit volume. So this is the difference you always have to uh, keep in mind. Now let me go to current. Current is equal to Q divided by T. So current would be NaVdT divided by E divided by T. So T and T is gone. I comes out to be equal to, remember these formulas, direct questions come from here. and J would be equal to I by A. So N A V D E divided by A and A gone. It gives me N V D E. So J is nothing but N V D E. This is the current density. Did you all understand this? Yes or no? Tell me. Tell me. Only few people are watching this video. So okay, no issues. Now let me go to Ohm's law. And Ohm's law, I told I didn't do the derivation. So Ohm's law, I told you that um, um, Ohm's law, I told you that current is proportional to voltage, or voltage applied is proportional to the current. And I told you that this proportionality constant is removed by writing a term R, where R is resistance of the conductor, and I gave you formula of R as R is equal to rho L by A. So if this is the conductor and rho is resistivity, resistivity, I told that it is the property of the matter, it is the property of the conductor. If the conductors are same irrespective of the cross sectional area and the length, resistivity will remain same. So resistivity is property of the object which remains same for the same object and changes as per the uh, as per the um, change in the conductor material. Now try to understand. I also gave you this formula where R is equal to R naught 1 plus alpha T. So I told that R naught is resistance at T is equal to 0, where T is temperature and alpha is uh, constant. So I told that R increases as T increases. Now, any particular material which follows Ohm's law, there are not all conductors which follows Ohm's law. So for conductors which follows Ohm's law, the graph is something like this. This is V and this is I. V is at Y axis, potential difference is at Y axis, I is at X axis, and because this is a straight line, I can compare it with Y is equal to mx. So this R will represent M. So this slope will give R value. So V is equal to IR. So for conductors following Ohm's law. So as we have studied Ohm's law over here, let me get into uh, resistance in series and parallel. So resistance in series would look something like this. I have already explained you that uh, resistance in series means same current should pass through same current should pass through all the registers. So if this is R1, R2, R3, and current which is coming out of here is I, so I can write that V. Now what did I have told you time and again that as this is revision class, I'm not getting into that concept once again. I'm just telling you the concept. I'm not explaining it. That um, in direction of current, potential decreases or increases. Write it down in the comment box. Let me check how many of you remember it. In direction of current, potential decreases or increases. Write it down in the comment box quickly. Okay, good. Decreases. So potential decreases. So if I start from here, V minus what? How much would be the decrease here? I R1 minus I R2 minus I R3 is equal to 0. So V is equal to I R1 plus I R2 plus I R3. So V by I comes out to be equal to R1 plus R2 plus R3. And what is V by I? V by I is circuit resistance, the equivalent resistance. So I am writing it equivalent resistance. So I saw that equivalent resistance when it is in series is summation of all the resistors in series. So R1 plus R2 plus R3. Now when they are in parallel, so I've told that in parallel combination, the potential difference among them is same, but current will get distributed. So if I is coming from here, this will be I1 plus I2 plus I3. Now I have also taught you Kirchhoff's law. So by junction law means, as I have told you in the class, junction law means, or I told you point law, where all incoming currents and all outgoing currents, summation of all incoming currents is equal to summation of all outgoing current. So if I take this point P here, the incoming current is I and outgoing currents are I1 plus I2 plus I3. So if this is V, I can be written as V by R, and I1 can be written as V by R3. I2 can be written as V by R2, and I3 can be written as V by R1. VV gets cancelled out. This is R equivalent. So let me write it R equivalent, and I am writing here P because it is in parallel, which is equivalent to 1 by R1 plus 1 by R2 plus 1 by R3, and likewise. So it goes like this. So this is series in um, resistance in series and parallel. Now let me teach you Kirchhoff's law. I'll just repeat it for you. So Kirchhoff's laws are, first law, you all know, this is junction law, And I just told you junction law, all incoming currents at one point is equal to all outgoing ones. And second one is loop law. So I have explained that loop law to you in the class. I am writing it. The algebraic sum of all the potential differences along a closed loop in a circuit. You write it down, 0. So what I do is I take a closed loop like this. So it's something like this. Suppose this is R1 and this is E1, this is R2, this is E2, this is R3, this is R4, and this is E3. So by Kirchhoff's law, the algebraic sum of all the potential differences along a closed loop in a circuit is 0. How do we apply it? So we take a point. Suppose this point is A, and we start from this point. So suppose the current is flowing in this direction and I'm moving in this direction. So I'm going, the current is flowing in this direction. So VA, I start from here. The potential difference would be what? If I'm going in the direction of current here, so it will be minus IR2. Then again current is here, so I will write it here as minus IR3. Now I'm going from positive of a battery to negative of a battery, so potential will decrease, so minus E3. Then again I'm going in direction of current, so minus IR4. Then I'm going from positive of a battery to negative of a battery, so minus E4, sorry, minus E3. Then again I'm going from positive of a current to negative of a current. So something like this. You, if you want, you can take different currents also. I2, I3, I4, I3, I4. So because there is a battery coming in between, so you can write I1, I2, I3, and then you can write I4, R1, and negative to positive is plus. I'm going from negative to positive, so this is plus E1, and then I reach this point VA, so that is equal to VA. So VA and VA is gone. You can write like this: E1 minus, one second, this would be E2. E1 minus E2 minus E3 is equal to I1 R2 plus I2 R3 plus I3 R4 plus I4 R1, and likewise. So that's how the Kirchhoff's loop law is applied in a particular circuit. Is it okay? Then I have told you all those things, batteries and how they are connected. If they are connected in series, it will be E1 plus E2 plus E3. If they are connected in parallel, so you have to find out equivalent resistance and equivalent um, potential. So I'm not getting into that. So let me do Wheatstone bridge for you. So Wheatstone bridge is something like this. I've told you. Um, it's something like this. We have a galvanometer here, and we have a battery. And suppose this is R1, R2, R3, R4. It becomes Wheatstone bridge when the current in the galvanometer is zero. So sometimes I replace this galvanometer with resistance, and it is asked that for no current to pass through this particular resistance, uh, what should be the I mean, out of there are four resistances R1, R2, R3, R4. So out of these four, three would be given to you, and it will be told that for no resistance here in this circuit, which is bifurcating R1 and R3 from R2, I4, which is separating it. So what should be R1 or R2 or R3 or R4? So I have done that for you. So do you want me to? Okay, let me do it. Let me not ask you, and let me do it for you. So what I do over here is I mark these points. So this is A, this is B, and this is C, and this is D. Now try to understand VD minus VC is equal to, suppose a current um, IG flows here. So it will be IG into R. Now, as there is no current at Ig is equal to 0, Vd minus Vc would be equal to 0. It means that Vd is equal to Vc. That I have already proved. Now, try to understand. So, let me write Va minus Vc. Suppose a current I1 I comes from here, and a current I1 goes here and I2 goes here. So I can write is I is equal to I1 plus I2. Now Va minus Vc is I1 into R1, and Va minus Vd is I2 into R3. Similarly, Vc minus Vb is I1, because no current goes here, so I1 would be here also and I2 would be here also. So I1 into R2, and Vd minus Vb would be equal to I2 into R4. So what I write is, look at here, I want to cancel out current. So I1 I will cancel out by dividing it. Um, Vm minus Vc divided by Vc minus Vb is I1 by R1 divided by I1 by R2, and Va minus Vd divided by Vd minus Vb is equal to I2 by R3 divided by I2 by R4. Now try to understand what is the difference on left hand side. Left hand side, here it is Vc and here it is Vd. So I can write that as Vc is equal to Vd. I can write this as Va minus Vc divided by Vc minus Vb is equal to I2 by R3 divided by I2 by R4, and this I2 gone, here I1 gone. So look at here, left hand side at both the places are same. So here it is Va minus Vc as LHS is same. So R1 by R2, RHS would also be same. R1 by R2 is equal to R3 by R4, or I get R1 R4 is equal to R2 R3. So this is the condition for Wheatstone bridge to be formed. Did you understand it? Yes or no? Now let me move to the capacitors. So okay, let's do one thing. Let me check how many of you just let me check how many of them just came for writing their names, and after writing their names they just disappeared. So I can see that now at 2:43 um, Harshini is there, Bhumika is there, Ritu is there, Ruchita is there, Shraddha is there, Shruti, Vaishnavi, Dev, Medhans are there. Others are not there. Okay, no issues. Fine. So let me just revise capacitors for you, and then I'll um, go to the questions. So capacitors, I told, a device which stores charge. So capacitor is generally denoted like this. I have done in the class at very elementary level. So I told that charge stored. So I told that generally we have plates like this on which I there is some potential difference which is applied here, and so it will be something like this. Q is equal to CV, where C is capacitance, and capacitance is denoted by epsilon naught A divided by D, where epsilon naught, we know what it is, permittivity of vacuum. A is equal to area of the plates. So you can see I have made plates here, and D is distance between the plates. So remember these two formulas, very handy. There would be questions on these formulas in your test. Now try to understand that when capacitors are in series and parallel, what happens. So if capacitors are in series, So what I write over here is, so this is the capacitor. Again, I'm taking three of them, and this is connected to the battery source, and this I am assuming it to be B. Now try to understand, these are the three capacitors with capacitance C1, C2, and C3. Now please understand that suppose if this is point P and this is point, uh, suppose this is point Q, this is point R, and this is point S. So look at here what happens. So point P and S are terminal points. Why? Because a battery has been connected across it, and then the charge will be supplied. So suppose this particular, because this is the positive size, this supplies charge plus Q here, and if charge plus Q is supplied from here, we can assume that minus Q is going from the other side. So it is, this is given to the last plate over here. Now, if this is plus Q and this is minus Q, how will charges get transferred from this first? So I'm assuming it to be plate 1. This is plate 2. This is plate 3. This is plate 4. This is plate 5, and this is plate 6. Now try to understand, the charges are only supplied to plate 1 and plate 6, and the charges doesn't get supplied to any other charge from the battery. So what is the phenomenon in which, or what are the different circumstances in which the charges are getting transferred from one plate to another plate? How does it happen? So try to understand, charge plus Q is supplied from the battery to plate 1, and charge minus Q is supplied to the battery from the battery to plate 6. Now what happens, the charge plus Q appears on the plate 1. Now, by induction, I have told that, or so here minus Q will go here. So the facing surface of A2, I mean the plate 2, will have minus charge to balance it. So I told you how it happens by induction. And then plate A2, plate 3 is connected to A2. So as minus q is appearing on 2, so electrons are drifted. So what happens, how this becomes minus, because electrons, to control this plus charge, electrons are drifted from electrons. So I can write here drift of electron from 3 to 2. So that's why minus comes here, as electrons are drifting from plate 3 to 2. So this will be plus q here. Again, as plus q is coming here, electrons would be drifting from plate 5, and how much, it will be minus q. So what comes here, plus q. So you should understand that electrons are drifting from plate 3 and plate 5 to plate 2 and plate 4 respectively, and that's why plate 2 and plate 4 will have minus 4, and plate 3 and plate 5 will have plus 5. Now how to calculate it? So you try to understand over here that Vp minus Vq is equal to, I have told that Q is equal to Cv, where V is potential difference. So potential difference is equal to charge Q divided by C1. Similarly, Vq minus Vr is equal to charge Q, because charge remains same, but the potential difference is, but the capacitance is different, since potential difference would be uh, different. And Vr minus Vs is Q divided by C3. So what I can write over here is, I will add all of them. So this Q will get cancelled out, R will get cancelled out. So Vp minus Vs, which is equal to nothing but the potential difference V, is equal to Q divided by C1 plus Q divided by C2 plus Q divided by C3. I can write this V as Q by C because charge Q is getting transferred from this battery. So Q divided by C equivalent is equal to Q by C1 plus Q by C2 plus Q by C3. And that's why the Q gets eliminated. So I get 1 by C equivalent is equal to 1 by C1 plus 1 by C2 plus 1 by C3. So this is in the series. I'm doing it when they are in parallel. So in parallel combination, so in series, when resistances were in series, yes, that is area of plate. A is area of plate. A is area of plate. Ruchita, I didn't see your chat before. In parallel, C is equal to omega naught A by D. This is area, and this is distance between the plates. And omega naught you know already. So these are, if this capacitance are in parallel like this. So uh, I was explaining about how it is similar and different from resistance in series and parallel. So in resistance in series, the current was same. Here the charge is same on all the capacitors. So if capacitors are in series, you should know that the charge would be same on all the capacitors. But how it is different in if the resistors were in series, R equivalent was equal to sum of all the resistances. Here it is different. Here it is um, we have taken 1 by C equivalent is equal to 1 by C1 plus 1 by C2 plus 1 by C3. This is C1 plus C1, C2, C3, and this is V. I know that as they are in parallel, the potential difference across them is different, but sorry, it's same, but the charges would be different. So if charge Q is transferred from here and minus Q is transferred from here, here it will be Q1, here it will be Q2, and here it will be Q3. So what happens is Q is equal to Q1 plus Q2 plus Q3. So what I do over here is, so Q would be equal to CV. So I write C equivalent is into V is equal to Q1 will be equal to C1 into V because potential remains same. Q2 would be C2V and Q3 would be C3V. V get cancelled out. C equivalent comes out to be C1 plus C2 plus C3. So here also how it is same from resistors perspective, that if resistors or capacitors are in parallel, the fundamental is the potential difference across those capacitors will remain same, but the charge would be different as the current was different in case of resistors. So C equivalent is equal to C1 plus C2 plus C3. So this is what from my side. One more thing which is left out is the heating effect, which I'll tell you. So that is nothing but, just look at here. So try to understand the concept of power. So first let's find out Joule's law of heating, and then I'll go to power. So I have already told you these things, so don't worry that I have not taught these things or something. So Joule's law of heating. I've just not told it. Joule's law of heating. So I know that work is equal to Q into potential difference. So what is potential difference? Potential difference is V, and what is Q? Q is equal to I into T. So I know that V is now, as a resistance is there, V is equal to IR. So I can write it as IT into IR. So work done is equal to I square RT. So what is this work done? This work done is nothing but the when the current passes, for current to pass, certain amount of work is done by the potential difference, by the battery source. And what is that? That is equal to charge transferred multiplied by potential difference. So that work done comes out to be I square RT. And this work done, this energy is wasted in form of heat. So we also write it as heat produced is equal to I square RT. So always remember that if I am giving you a loop something like this, and I am telling you that this is suppose potential difference, and this is 2 ohm resistor. I am saying that find out the heat produced in 2 ohm resistor. So R here would be 2 ohm. I'll not give you I'll give you all other resistors. Suppose this is 1 ohm and this is 2 ohm and this is 10 volts. So what I'll give you is that I'll give you this kind of circuit, and I'll say that in this 2 ohm resistors in 3 seconds how much heat would be generated. So what you have to find out, you already know R. You have to find out by loop law, applying loop law and equivalent series and parallel resistors. You have to find out I here. Once you find I square, multiply it with R, and T has been given to you. So you will find out how H can be calculated. Now I know that work done, what is power? Power is equal to work done per unit time. So it is I square RT divided by T. So power is equal to I square R. So here only I can give that how much power is originated here or something like that. I can also write it as I into IR, and IR is V. So power can be written as, one second, power can be written as IR is V, so this can be written as V into I. Now, if V is equal to IR, I can be written as V by R. So power can also be written as V into V by R. So power can also be written as V square by R. So that is how, okay, I'll repeat work done. Look at here. Work done, I already told you, is work done is equal to, let me write here, work done is equal to charge into potential difference. So which is Q into V. So that's what I have been writing here. That work done is equal to charge into potential difference. So Q into V. And Q is nothing but Q is equal to IT. So I am writing it IT. If V is there, so V is equal to IR. So work done is equal to I square RT. Now what is work done? So if current is passing through here, so to let this current pass from this resistance, some work needs to be done. There is some uh, hindrance in the path of current. To overcome that hindrance, this battery is doing certain amount of work out here, which is um, potential difference into IT. So what is potential difference? I into R multiplied by I into T. So this comes out to be I square RT. Now how this work done is wasted? So this is wasted as heat energy. As the current is passed through this particular resistor, there would be certain amount of heat generated in the resistor, which is called I square RT. So I square RT can be written as heat generated or heat produced in the given resistor. Heat produced in the given resistor is proportional to the square of the current flowing through it. It is also proportional to the resistance value, and it is also proportional to the time for which the current is flowing through that particular register. Remember, if a glass bulb is there and it is on for certain time, you go and touch it. Don't touch it. I'm saying just for the matter of experiment. Just don't go and touch a white bulb. Your hand might burn. So if you just feel it with the help of certain cloth or something, you will find it to be heated. Why does it get heated? It get heated because certain current is passing through that filament of the bulb, and the because of the current passing through it, there is some I square RT heat is getting generated through it, and that heat is making it um, making the temperature of the bulb rise. So that is why you feel it to be hot. That's it. So this is what power is. I hope Shruti, you understood everything out here. If not, let me know. Let me know, all of you. This is the last concept. Okay. So somebody is saying Shruti still have not. Okay. She replied now. Can I solve one question on heating effect? Okay, let me solve one question. So give me a moment. I have sheet number one and sheet number two. I don't have sheet number three. Okay, chalo. Um, I'll solve it. Which sheet, Ruchita? Which sheet? Question number 29. Which sheet? Tell me the sheet number. I'll solve it. Ruchita, I'm asking which sheet number? Okay, sheet number three. Okay, just let me just find out sheet number three for you. Okay, so this is this is question number 29. This is the question you are asking, Ruchita. Tell me. Okay, before she replies, I'll solve this question number 29. In question 25, somebody, Bhumika asked me to, okay, Ruchita, I'll solve question 29, don't worry. In question 25, find the heat developed in 3 seconds. So let me write it here for you. In 6 ohm resistor, find the heat produced in 3 seconds. Solve it. We'll solve this question and then we'll solve question 29 and then we'll wrap up the session. Done. Done. Okay, let me check. Give me the answer. Okay. Make this diagram on your notebook. I'm doing it on. It's something like this. Okay, so let me solve this question for you. Uh, this is 4.5 volts. This is 3 ohms. This is 6 ohms. This is 10 ohm, and this is 3 volt. So suppose a current I originates from here. So this goes as I here, and it gets separated into two parts, in two loops, I1 and I2. So by junction law, I write I is equal to I1 plus I2. Now try to understand, I have two loops, so I'm applying loop law. I'm taking this point a junction, and I'm taking, so suppose this is point A. So VA minus 3I minus 6I1 plus 4.5 is equal to VA gone. I can write that 3I plus 6I1 is equal to 4.5. Now I go to this loop, suppose this is point B. So I write it VB minus 10I2, and I'm going from positive to negative, so I write 3 volts, and I'm going in opposite direction of current, so I write plus 6I1 is equal to VB. So this and this gone. I write 6I1 plus minus 10I2 is equal to 3. Now here I1, I2 are there, and here I is there, so I will convert it into I1, I2. So this is 3I1 plus I2 plus 6I1 is equal to 4.5. So I write this as 9I1 plus 3I2 is equal to 4.5. So I write here 9I1 plus 3I2 is equal to 4.5. So I multiply this with 1.5 because I want to make it 9I1. So try to understand, if I multiply this with 1.5, so I get 9I1 uh, minus 15I2 is equal to 4.5. So I subtract it, this becomes positive and this becomes positive. 18I2 is equal to 0. It means that I2 is equal to 0. If I2 is equal to 0, let me put my value here. It comes out to be 6I1 minus 10I2 is equal to 3. So if I2 is 0, 6I1 is equal to 3. I1 is equal to 3 by 6, which is 0.5. Now try to understand, I am asking in 6 ampere. So 6 ampere current is not 0. In 10 ampere current is 0. So 6 ampere, the heat would be equal to I1 square multiplied by 6 into 3 seconds I have asked. So this comes out to be zero point 0.5 square multiplied by 6 into 3. So that comes out to be 0.25 into 18, which is equal to 4.5 joules. So answer is 4.5 joules. Now let me go to question number 29. Now let me go to question number 29. So just look at here. Question number 29 is this question, 483650. Okay. And I have to find what? Take the potential at B to be 0. Find the potentials at points C and D. If a capacitor is connected between C and D, what will be the charge? So this is the Wheatstone bridge. 4 into 6 is 24, 3 into 8 is 24. So as C1 C4 is equal to C2 C3, whatever capacitor you connect in between, the charge would be 0. This I have already proved. So I am only gonna solve the first part. What is the potential at point C and D? So try to understand here. 483650. So let me, 4836, it is something like this. This is 4, this is 4 microfarad, this is 8 microfarad, this is 3 microfarad, and this is 6 microfarad, and this is connected to a battery source of 50 volts. So this is 50 volts. So this is in capacitance is in series 4 and 8. So let me write it. Let me not do it with this method. C equivalent for series is equal to C1 C2 divided by C1 plus C2. So for 4 and 8, for upper circuit, this would be 4 into 8 divided by 4 plus 8. So how much it comes? 32 by 12. So it becomes 8 by 3. So this is nothing but 8 by 3. Now try to understand, this is 8 by 3, and similarly it would be 3 into 6 divided by 3 plus 6. So 18 by 9, this comes out to be 2, so this is 2. And so I can write this as 8 by 3 microfarad, and I can write this as 2 microfarad, and this is connected to a 50-volt battery source. Now try to understand this 8 by 3 plus 2, because they are in parallel. So C equivalent would be equal to 8 by 3 plus 2. So this comes out to be 8 plus 2 into 3 divided by 3. So this will be nothing but 14 by 3 microfarad. Now I know that. So it is something like this. Please look at here. I'm just, 1 second. It will be something like this. So this is 14 by 3 microfarad, and this is 50 volts. So Q is equal to CV. So 14 by 3 into 50, this comes out to be 700 by 3, because this is microfarad, it will become microcoulomb. Now try to understand, guys. From here the charge which is going is 700 by 3 microcoulomb. Now as they are in parallel, the charges will get distributed as per their capacitance. So suppose charge here is q1 and charge here is q2, so q1 will be equal to c1v and q2 is would be equal to c2v. So q1 is c1 is 8 by 3 and v is 50. So this is equal to 400 by 3, and q2 is 2 into 50, that is equal to 100. So this is microcoulomb. It can be written as 300 by 3 and total would be 700 by 3. So this is microcoulomb. Now try to understand, guys, here that this is q2. So this comes out to be as 100 coulomb, and this comes out to be as 400 by 2 microcoulomb, and this is 100 microcoulomb. Now as these are in series, so on both the capacitors this would be 100 microcoulomb, this would be 100 microcoulomb, and this is 400 by 3 microcoulomb, this is 400 by 3 microcoulomb. Now this is point b, sorry, this is point c, this is point D, this is point A, and this is point B. At I can write that VC minus VB. Q is equal to CB, so V would be Q by C. So Q by, suppose this is C1, C2, so Q divided by C2, and VB is equal to 0. So VC minus 0 is VC, and Q is how much? 400 by 3 divided by 8. So VC comes out to be 50 by 3 volts. Similarly, VD minus VB would be equal to 0. Sorry, not 0. So this is 8 by 3. VD minus VB is Q. Q is 100 divided by how much is this? 6. So this is 100 by 6. This also comes out to be 50 by 3. So this is nothing but VD is also equal to 50 by 3 volts. So I hope you all understood it, and this is what it is. So if you didn't understand it, let me know. Otherwise, I'll wrap up the session. Okay, thank you so much for joining the session, and wish you all the best for your upcoming test. Thank you. Thank you so much.